Hi everyone. We'll do a problem today consisting of a non-conducting sphere concentric with a spherical shell. So that's the spherical shell. Let's make it a little bit larger. Okay. So the inside, it's a non-conducting sphere, uniformly charged. So I have uniformly charged non-conducting sphere, and let's give it, for example, a charge of minus q. Okay, so the charge here is negative. And since it's negative and it's a non-conductor, so the charge will be distributed everywhere and uniformly distributed, since that's the condition. And it's minus q. And let's say the spherical shell, it's a conducting spherical shell. I have a conducting spherical shell. And let's say with charge, let's give it some charge, for example, 3q, positive 3q. So I have 3q on that spherical shell. Now, first thing to recognize that if the charge on the sphere is minus q, that minus q is going to attract to its side positive q, opposite. So I'm going to have here positive charge on the inner surface of the spherical shell, and the value of that inner charge is q. So for the spherical shell, I have q inner and the q outer. So q in is positive q because it should be opposite to the sphere at the center. Since the sphere has minus q, then this minus q will attract plus q. So what will be q out? The formula is q out, it's the q total, minus the q in. So remember that formula. Q out, it's q total minus q in. Then the q total was already given to us, which is 3q. That's the q total, 3q, minus q in, which is q. So it's going to be 2q. So inside I will have q, and on the outer surface, I'm going to have 2q. So we draw some charges on the outer surface. And we can write outside 2q. So we can check 2q plus q, right? 2q plus q will give us again 3q, which was the initial charge of the spherical shell. And since it's a conductor, so the charges will be only on the inner and outer surface. Now, the question is, I want to find the electric field everywhere. Okay, so find the electric field everywhere. Find the electric field everywhere. The formulas that we're going to use are proved by Gauss's law, but those formulas, let's say they are universal, so we can always apply them in case of uniform sphere or spherical shell, as we are going to see now. And let's name the radii here. For example, I'm going to call the radius of the small sphere, I'm going to call it, let's say, A. the radius of the inner surface, it's B, and that of the outer surface, it is C. Okay, so I have A, B, and C. Now, for R, for distance smaller than A, this means inside the non-conducting sphere or inside the insulator, so right beside it, inside the insulator, inside the insulating sphere, electric field, as we know, it's equal to K multiplied by the charge of the insulator or non-conductor times small r over capital R cubed, which is K, Q, small r, and this r cubed, it is the radius of the sphere, which is in that case A cubed. So this is the electric field inside the non-conducting sphere. And again, that's the formula, as we know. That's the formula. Now, between A and B means in this gap here, in this gap. And by the way, this electric field inside the spherical shell, it's going to be directed inwards because the charge is negative. So this electric field is simply inwards. Now, for R, so that's the case, the first case. Second, for R between A and B, means in the gap between the sphere and the spherical shell. So again, if you apply Gauss's law, which means if I take any imaginary surface here, and I apply Gauss's law, what is inside that Gaussian surface is only the sphere, the non-conducting sphere. And we already know what's the electric field outside the sphere. So the electric field outside the sphere is K. Electric field, it's K multiplied by the charge of the sphere, which is Q, over R squared. So that's the electric field between the sphere and the spherical shell. It's also inwards because the charge of the sphere is negative. Now, what's the electric field inside the conductor? Inside the conducting spherical shell. Remember, the spherical shell is a conductor. Here, conducting spherical shell. We already know that the electric field inside the conductor is 0. It's always 0. So inside the conductor means R, it's between C and B. The electric field is 0. Okay? Field is 0 inside the conductor. Inside the conductor. Last, I want to find the electric field outside the spherical shell and the inner sphere, anywhere outside. So if you take also, let's say, a Gaussian surface outside, any Gaussian surface outside, then what is inside that Gaussian surface are the spherical shell and the insulating sphere. So this means the electric field, so for R greater than C, I have two electric fields. The electric field due to the sphere and the electric field due to the spherical shell. Spherical shell. So the electric field of the sphere, as we know, it's K Q over R squared. But this electric field is inward. So inward, because the Q is negative, it's a negative charged sphere. Because it's inward, so I put a minus. The electric field of the spherical shell, it is K multiplied by the charge of the spherical shell, which is 3Q positive, divided by R squared. Positive because it's a positive charge means outward. So the figure, if you want, it looks like that. That's the spherical shell, which is negatively charged. That's the that's the inner sphere, and that's the spherical shell. So the spherical shell, it's positive, as we said. This is positive. And the sphere, it's negative. Here it's negative. So at any point outside, the sphere makes an electric field inward, while the spherical shell makes an electric field outward. And you can notice that the red electric field is bigger than the blue electric field, because you can see the charge is bigger. Here 3Q, while here it's Q. So the net electric field is going to be away or outwards. Finally, the answer here, the net electric field will be 2kq over r squared, and it is outward. Again, why outwards? Because the red E, it's bigger than the blue B. So it will follow the direction of the red electric field. Okay? And this is how we solve the problem that consists of a spherical shell and an insulating sphere inside. Thank you for watching.